I have here a Mark II Pumpjack, and I want to show you how to add loading from the polish rod, sucker rod, and how to generate some meters of interest. This is not exactly the one you saw in the recording on how to import shapes from AutoCAD via the DXF format, but nonetheless will be useful for you to watch the several explanations here. So I'm going to delete and add them again to where we can see how so split, and I'm going to I said delete, split, and explain what we have here. So this is a rectangle, and I created it vertically, and this is a rectangle created horizontally. This is the crank. I set it to 0, so I changed my mind. I'm not going to delete. I'm going to explain to you what we have here. So originally the Pumpjack was a simple 4-bar, and well, you're seeing something else here. So yeah, it was a 4-bar, was a crank of length R2, is determined from other analysis, to which I'm going to add this rectangle here. So I use this half rectangular joint, snap it at the end, and another half rectangular joint and snap it at the end of this segment, and hold the shift key and join. So now I have an extension to the, setting to angle 0, to the crank. There's the motor, was there like before. Well, it was there before. So, and then window properties, or rather edit, select all windows, appearance, and show. Okay. So I have everything visible now. The this one here, it just shows the center of mass from the appearance function, and what you see is a square that is a half of a joint like this one, and I said so it was deleted. Okay, so half a joint, and then another half joint, and I'm connecting them together. This will be the counterweight. Okay, so I have the counterweight that will be adjusted to produce balancing. I do the simulation with in reverse, so this was actually something that when this was a complete simulation was added towards the end. Okay, so I have using the define new control, generic control, something that you're how to do, and then I made it into a text box. I changed the limits, and so what I have this input 29, and this is the X of the connecting rod, and the other one was input 31. Okay, so let's see. Split, and this one is for the x-axis input 29, we said, and then I have for this other square point in the y direction input 38. Let's see, 31. Okay, so I'm changing it to input 31. Alright, so as I change these values, this is now this the half the origin of the local reference frame to this link. Let me change its color to something that can be distinguished easier. Okay. And again, this is the counterweight. So by changing these values, and the length is 1.7, let's make it 1.6, and okay, so x of, oh, by the way, I need to show their names to these Windows appearance show name, and to this one too, Windows appearance show name. I removed the names, and that's why. So x of counterweight, if I make it negative point, so half of 1.6 is 0.8, it goes all the way to the ends. If I have it 0.8 goes to the other end, the 0 is in the middle. As for this one, it has 1 meter, so this can go to from negative 0.8 to 0.8 on one hand, to such that it doesn't come outside of the, you could actually define a point that's outside of the surface area of the body to which is attached. Okay, and this one would be from negative 0.5 to negative 0.5. So if I change this to 0.5, it went to the top, and if I change it to negative 0.5, it goes the other way. So let's put it back to 0. Okay, let's see, 0. What's wrong with you? So this is input 31, and we have input 31. I don't know why it's not following. Oh yeah, it was a matter of just reminding the point to follow the control. Okay, so join again. I can move this to negative 0.8 and then negative 0.5. Well, this it tries to follow, as you could see. So 0 and back to 0. Okay. So what why I'm doing this? At some point we're going to move this counterweight in and out, up and down, until we minimize the fluctuation of the motor torque as it's driving the pump jack. I don't have. I need to show the name. So it says rack coefficient. Okay, so let's go to the load now. So I have here a little disc, but of heavy mass, 700 kilograms. I calculated this as or you will calculate this as the weight of the rod, the polished rod made of steel, plus the difference in volume would be oil and water. Make sure you need to do some research what would be the density. You can assume it's 50-50. Oil, of course, is lighter weight, like 0.8 tons per cubic meter, or 800 kilograms per cubic meter. Water is, of course, 1 ton per cubic meter. Anyway, so I the mass that I chose for that disc was 700 kilograms, and it's attached with a pair of this kind of joint. So one, and then on the disc another one, again smaller, just to prevent them from rotating, and then we join together. Okay, but of course I don't need them, have one already, and it's here, so it's jointed. They're jointed together, joined together, and then what else? I define the force. So you use this force function and you place it like right here. I'm doing it elsewhere to where you can see. And then we have what? Zero vertical component, or the horizontal component, so it'll be vertical force. And then for the this says drag coefficient, it's input 35, so I'm going to go and for the 35, this is a starter, it's not all, so input 35, and this gets the drag coefficient gets multiplied with the velocity of this point. So this point is 0.32. What I'm explaining here, it's already implemented. There's a force that is attached together with the at the center of this little yellow disc. What I'm doing it again here so they can see. So one more time, this is 0.32, and the way we refer to them is okay, so what I did quickly was to just click on the point, measure velocity, and what are the options. So I have velocity 0.32, yes, velocity in the x direction. I don't care, velocity in the y direction. I'm copying this, and I no longer need the meter really. So for the force now, I have the drag coefficient and then multiplied by the velocity of the point in the y direction, and this opposes motion. Okay, so if I hit run, I will see two forces of same magnitude. And you can define vector length, by the way. So I have forces and I can make them short now, 5 times shorter. Let's see. So hit run, and as you can see, they behave the same. One was already there, and I'm going to just delete what was added just to explain to you what needs to be placed. The force, really, the force that needs to be placed at the horse head to simulate the viscous damping that's going on as the polish rod is pulled in and out of the ground. You are expecting, of course, to have less drag, and we can include that effect if we want to, but we're going to stay with just the same drag coefficient for both the upper stroke and the lower stroke of the horse head. Okay. All right, so one more time, this is a text box that I can adjust this drag coefficient, and we'll experiment with it such that we dissipate the motor power. Otherwise, for one full cycle of the pump without any dissipate effect, working model being an ideal environment, the average power for one full cycle of the pump would be 0, and likewise the average torque. The motor here, so let's see, the motor is just one. It's of the velocity type, and this is You don't see it's outside the recording area, so it's in radians per second. The radians per second were calculated correspond to certain number, I don't remember, strokes per minute of the pump. Okay. All right, so we have the effect of the weight of the sucker rod, and then we have the effect of the viscous drag as you move the sucker rod was surrounded by oil and water in and out of the ground. Okay, I have we'll discuss these. So they are the menu buttons, and I have one that's a racetrack. How do we racetrack? Let's see, a racetrack. So I've got this one. Click on it, and it's, I don't need it. I have one already. And then I have another one, define new button, menu button, and this is clear meter. Raise meter value is this one. Okay, but I renamed it window appearance automatic name, and I said clear meter. It's what I did, and change the column, rather color. You can do that too. Windows appearance color, and I can make it any color I want. Okay, but again, they exist, and you'll see their use as we play some scenarios. Come on, I want to delete you. Okay, so yeah, I have two menu buttons that are here, and controls. The drag coefficient, the units are Newton per meter times second. So when you multiply with velocity, will be, so again, Newton second per meter. So when you multiply with velocity, it gets you Newton. All right. Okay, so 1, 2, 3, 4 controls, and two menu buttons. Okay, let's add some measures. So we want to record the rotational graph, that is position. Let me save. Position of the walking beam. Okay, and I want this to be as function. So let's see, measure position rotational graph. Not that I need this one, but this is, the crank is body 38, and so instead of time I have body 38, and this is theta 2, and this will be theta 4 right here. But I want them to be in degrees, so multiplying by 180 divided by pi, both of them. Okay, of course this is no longer true, so I go to Windows Appearance, and I don't want to show units. Actually could, like here, could be the units included. This is because I have rotations radians rather than degrees. Okay, so this is window appearance rotation of walking beam. I don't know why I deleted it. It was walking beam 1. Okay, so we have rotation walking beam, and let's see. Of course, we need to scale it. So it goes from 0 to 360, and then it goes from whatever that value, so minus 20 to 20 degrees. Let's see if it's enough. Possibly. Okay, you can see I unchecked the auto scaling. So we have the meter for the walking beam. By the way, I have a pause control that it pauses when the crank, that is body 10, is greater than 2 pi. This is body 10. This is body 38. Which one is body 10? Yeah, well, this is how I mean, originally the crank, so I can change it to body 38 if I want to. So originally the crank was the gray link and wasn't assembled from 2 pieces. So some improvements to an original model that I had built. Okay, so we have the rotation of the walking beam, and I could let's see. I'm not sure if the newer version, the one available on engineering computers, are torrent to this kind of editings. But the newer version might not be. This is radians per second, and this is d theta 4 over dt, and this would be body 1 position rotation. Instead I have body 1 velocity rotation, and this would be for like a secondary axis. Let's see. A secondary axis. I'm not sure why it's not showing to the side. So minus what? 0.1. 0.1. Well, so we have this edit. I can say duplicate. Okay, it's what I wanted, and we'll delete this, and then go here and delete this one, and we're left with the acceleration. Come on. So theta yeah, you need to remind working model that we made some deletions. Okay, so I have this will be the velocity, angular velocity, Windows appearance, angular velocity of walking beam, and this would be, let's say, auto. Just so run. Well, I said auto scale. So for one thing, it goes from 0.4. Let's see, negative 0.4 to positive 0.4. Maybe the more negative 0.5 to 0.5, and so we have the position, we have the velocity of the walking beam. This will become a little bit busy with graphs. If I want the acceleration, edit, duplicate, and for accelerations we'll just change this to acceleration, and then this goes d2 theta over dt squared, and let's see if I hit run. Okay, so it'll be negative, the limits -1 to 1 possibly, and this of course is Windows parents Windows appearance, I said. Okay, here it is. Okay, the radians per second squared. Maybe use the sign. So I have plots for position, velocity, and acceleration of the walking beam, and they should match very closely the Excel spreadsheet. I'm expecting to see them, side by side, or in your report side by side, to where you validate the working model. You validate with working model the Excel spreadsheet. Okay, and then to plot the transmission angle, you need to make sure that when this is 0, so I create it as a horizontal piece, remember, and rotate it in place with half joints like here, or rather this, and then connect it. Alright, so that can do this now. Join, and this is 0. Okay, so this guy is the angle. So measure position rotational graph. So this is body 11, and then let's keep this one. So this will be a plot of, why do that? Let's go with this route. Edit, duplicate graph or meter, and we're going to show transmission trans angle. Okay, so we have the transmission angle, at least formally. So what is that going to be? Body 11 position rotation. Actually, could have saved that, and then decided it's body 1. Okay, so remember from other discussions that we had, so from theta 3 we subtract theta 4, and that will give us the transmission angle times 180 over pi, to have it in degrees, just because in my case units, numbers and units are, so for rotations I use radians, not degrees. Okay. Alright, So let's see, transmission body 11 position rotation. So one is body 1. The walkie beam is body 1. The connecting rod is body. So now I shall see the use of the clear meter. And transmission angle usually goes to 90 degrees, or at least what I remember from come on. So body 11 and body 1. So body 11 position rotation, body 1 position rotation times 180 over pi. And if I make this, let's see, 0, 0, and he'd run. What's wrong with you? Okay, minus 90 to 90. Might be a glitch in the meter itself. It's rejuvenated. Nothing happens for some reason. That's no problem. We can copy this to Notepad. So I open the Notepad to save some equations here. And then this one. Where's Notepad? And alright, so I have the Notepad, and I define a new meter. So let's see, or rather duplicate. Duplicate, and let's see now. Looks like wasn't. Well, minus 180 to 180, maybe no. Nothing. Okay, let's look at the values. So run. Split. So if I make this 0, and then this one, I make it 0. And let's so join. And this angle is 1 point. This is 90 degrees, near 90 degrees. And this is body 11, yes, and this is body 1. What am I doing wrong? So body 11 position minus body 1 position rotation times 180 over pi. Minus 360. 360. Oh, it's somewhere there. Not sure why it ended up so negative. So it was there all the time. I'm sorry for the spending too much time on this. And why position rotation? I can put a minus in front, move it up. And it's still negative. Doesn't make sense to me. Okay, well, one thing we could do is just look at the body 11 rotation in degrees and see what the values are. So going from 0 to 180. And all to create a plot of the transmission angle. Okay, so this was this angle, the angle of this link, body 11. And then I have this other, so it's body 1. Let's look at the values. So yeah, they make sense. Will be essentially this graph. Now, if I go and the way I had it, body 11, body 1, converted individually to degrees. Yes. So it looks like the reason was that in a parenthesis? It did not work. So I had body 11 dot position dot rotation, my body 1 dot position dot rotation, everything multiplied by 180 over pi. If you multiply them by 180 over pi individually, looks like we get the desired result. Okay, so from 0 to 90 degrees, looks like it can be from 50 to 90 degrees. And we have a plot for the transmission angle. More than half hour spent up to this point of the recording. Okay, so this is all kinematics. And again, you should compare spreadsheet Excel with the working model and to validate the spreadsheet. What we're left doing now is to plot the motor torque. So I select the motor and it's selected, and then I say measure torque transmitted. So the type of motor is RPM, and again, everything will be not function of time but rather crank angle. So theta 3, rather 2. Right, and going from 0 to 360 on one hand, clear meter, racetrack. So let's look at the values. Yeah, it's pretty big. So I'm looking here, Newton meters, 10,000. Minus 1 E4, and the other one would be plus 1 E4. Even more. So let me make this 2. And I can make this smaller. Delete 10, put a 5. Nope. Mistake. So this is the motor torque. Now for torque at motor. So if I go to appearance and I want to show the x-axis, you could do it for any of the graphs. So yeah, the x-axis. If you look at the area that's above and here that's above, currently, so for one full cycle, you'd expect the two areas, the positive area and the negative area, to be equal, or the total area under the curve to be 0. Again, I don't have any, or do I? Well, I'm sorry. So if I change this to 0 now, then what I just said, it applies. So positive area and positive area with the negative area is there'll be 0, or area under the curve between 0 and 2 pi of crank rotation 0, because I don't have any dissipation of work during the cycle, the full cycle of the pump. And we said that we're going to, so this is a graph that we'll be monitoring, and we're going to add damping, that is drag, viscous drag, such that the graph, the torque graph, shifts up 15-20%. So we look at the graph appearance. I have an upshift. If I instead clear meter values, so 0 again, run. Yeah, it went run. So it keeps just the by pressing the clear meter, keeps the latest value. So let's make 2000 instead, and I hit run, and this is probably, let's say going from 10,000, 15,000, so back to 0 to where I have the reference, and then I'm choosing a value between 1000 and 2000, 1500, and I hit run, and I'm going to stay with this. Of course, there was the counterweight, so let's take that back, put 0, and a discussion is due about these masses here. So this was the, again, 700 calculated value for the weight of the sucker rod and oil and water mixture. The walking beam, 200. It should be realistic value based on the size of the pump. So 200 kilograms might be too little for 3-story high Mark II pump jack. The crank, mass of the crank is less than a kilogram. So you know, this also is massive. It's tens of kilograms at least, if not more. So 20 kilograms for the crank. This other one 40 kilograms, and the horse head itself, actually in the project specifications I'm saying that assume that at first that there are thick plates made of steel made of steel in certain thickness, because masses matter. Okay, as for the the effect of the counterweight, actually I'm going to make this was 40 kilograms. I make it a small 0.1, and then I make this 0.01 negligible counterweight, and no damping. So this would be the motor torque that is not held by any counterweight, and no damping. Now we said that 1500 would be some value, okay, to shift the curve, the torque curve up by 15-20%. And okay, so now I have the damping chosen, no counterweight. How big should be this counterweight? Again, they are massive. They might be, half a ton. They come in slabs, and they are lifted in place, bolted. You should go back to the photographs of Pumpjacks to have an idea. Anyway, so let's say this is 100 kilograms. Doesn't mean that and my pump is really small. So if you just look here, it's like what, 5 meters versus the bigger ones that you might find. Anyway, so I have a counterweight and I hit run, and I want to see the effect of having a counterweight, and it does have one. Okay, so you can change the counterweight, but also you can change the location. So I can move it further out. That was -1. It stops at -0.8. Yes. So let's see now. Reset. Or if I go the other way, 0.8. What is the effect? Not much. Clear meter. Let's have a reference. So negligible counterweight goes to 0 and 0. Hit run. Okay, so this is the reference line. Here's a way you can change the color, Windows appearance, color. Alright, so we have a value. And if I change this to 0.5, let's see what effect it has. Well, it's still a reset. It's a small value. But if I make it 100 kilograms, if I make it 200 kilograms, if I move it to 0.8, no, -0.8. Okay, so I'm getting there. Alright, so I make this again 0.001 to have a reference of the torque without a counterweight. Again, this area and this area and this area will be 0. No, I'm sorry. We have the damping. But this is the reference without a counterweight. So we have a damping, but I made the counterweight very small. Now I change it to, was it 100 kilograms? And Heat run. But if I make it 200 kilograms, I'm getting the, well, if I make it 300 kilograms, it is getting even better. So 400 kilograms. Mm, 500 kilograms. So with 500 kilograms, which is quite a bit of, well, 500 kilograms is not a few dumb, like what? A few good dumbbells, clear meter, and then, yes, and then I make this 0.01, no counterweight, just to show the difference. So what I wanted to say is that at this point we have a counterweight. Yes, so small fluctuation of the torque compared to the case without a counterweight. That's helpful to the motor. We can the average torque, or the peak torques on the motor would be less, and a smaller motor is capable of running the Pumpjack. So back to, was it 500? Run again. I make this 600. Yeah, it's getting probably 600. It's even better value. You cannot put a zero value. Actually, I have it this way. Oh, so a mass to body in working model, if you set it to exactly zero, it'll give you an error. It may even crash. So remember that. Clear meter, heat run. So we have damping, we have the socket rod weight, motor torque, and now if I make this counterweight equals to 600 kilograms, which is comparable to this weight, I have the least fluctuation of the crank torque, and you can stay with this. So at this point you can export the meter values, meter data, like you did, and pick it wherever it went. Okay, here it is. So what do we have? We have let me look at this. So we care about the motor torque. I closed it without saving. Well, I haven't modified it in any way. So we want the torque, the motor torque primarily. One thing you could do is just delete this, clear meter, run, reset, file, export, export, yes, I'm rewriting it. And then you're going to pick it up from where it was saved, and now we go to to Excel. Alright, so I'm in Excel. And I'm going to calculate the average torque. So let's see to where we can see the Excel. All right, paste. I don't care about these one here. So I have theta 2 in degrees. Is in degrees? Yes, it's in degrees. And the torque, I'll move them to the right, so that I can add a column in radians. Do we need it? So come on. Just copy, paste, and it's not saved. Okay, so here I'll add the column in, actually not, the column radians. Alright, so column in radians, I take the degrees, divide by 180 times pi, open close parenthesis. And okay, so what do we want to do is to calculate the average torque, something you did in one homework assignment. So traps, and it will be first is 0, the other one is here trapezoid times minus this over 2. No. What do you want from me? So over 2. Okay, so this is the individual trapezoids, and then I'm going to sum trapezoids. I'm summing trapezoids there. Okay, so these this is the work per cycle of the pump. If I want the average torque, which will be used to calculate the motor, to select the motor. So that will be the work equals divided by 2 times pi, open close parenthesis, close parenthesis. Okay, so this is joules, and this is average torque, Newton meters. Okay. So yeah, I've got the average torque. I can calculate for this Pumpjack. So the motor is motor. I'm looking at the motor now. 1.6 radians per second. So it's 1.6 radians per second. The power power in watts would be the average torque times 1.6 radians per second. So this is like what, 3.5 kilowatts, which is not too big of a motor. Okay, but of course you need to provide for an excess power. So 3.5, you're thinking maybe at least 50%, so 1.5, that's for 50% extra power. So yeah, 6.5, or rather 5.5, 6 watts would be, for my case, a good motor to use. Okay, so I guess this is it. And the steps being to, and I'm not going to save, rather close without saving, so I can still have the graphs that were there. I deleted it just to keep only 2 columns on the data. All right, so 1 hour and 1 minute of recording. You can play it faster, save time, but this was it. Oh, maybe not. Let's do this additional thing. So I click on the I-beam again. At some point you need to specify a realistic mass based on the I-beam selected. It's part of the project requirement. So you go here and you there is a script that says shear and bending. Okay, so shear and bending moment diagrams. You click on the beam. That's why the beam has to be native to working model. And stop has to go from here. All right, so it gives you a report of the. So one more time, script, shear and bending moment, and you hit run. And it draws for you the bending moment diagram, and it tells you what the minimum maximum bending moment is and when they happen at the t equals whatever seconds. And with these you're going to calculate well, first select the beam, an I-beam, and then proper is a fatigue analysis. The I-beam is this sizes will be hot rolled. You can choose one based on the maximum bending moment, and you're going to take a design factor of 2 or 3, so you choose the what are the 3 or 4, and then you do fatigue analysis according to Goodman. But for starters, you can take a design factor that is 3, working with the maximum bending moment, and then you do fatigue analysis for infinite fatigue life of the I-beam. Okay, so this was the last part that I had in, almost forgot, but you need to include it in your project. Okay, so recording stops here. I'll upload it for you to watch. Thank you.